Hi, welcome back to Introduction to Computer Networks. And you guys, look at the schedule for the semester. We are now in week 12. And you see, this is actually the fourth last lecture or fourth last week. So we don't know whether there's going to be lecture necessary the last week. Okay. So essentially, after this week, just a few more weeks to go. This week, by Saturday, we do have a few assignments doing, but all of these are quizzes. So this is going to be quiz 30 to 33. But as a reminder and an unofficial announcement, PA number 8, it will be due next Saturday. And the reason that I would like to remind you to start working on PA 8 probably this week is that it's less trivial as a PA 7 if you want to do it the harder way. Okay, the harder way generates actually shorter program. Okay, that is to reuse the existing code in Golan's web server implementation. Okay, so I would really like to see more of you trying to implement it the hard way, which is to explore and reuse some of the existing code in Golan already. So try a little bit earlier. Okay. And yeah, of course, hi Wei Xiang. And thank you very much, Michael, for the very sweet message. Yeah. All right. So I hope that you will like the other layers, like transport layer or the application layer as well. Sorry that the semester is so short that we won't be able to cover link layer. But it's something that Polly is working on. Okay, thank you. And yeah, good afternoon, Sean. And today, okay, we actually break open chapter 4 last week already, but many of you are probably a little bit anxious about the second exam. So I'm not sure if you follow the overview of chapter 4 entirely, but a quick recap. Okay, if you recall, in transport layer, we do have two services, TCP and UDP, right? Okay. In fact, the service that are used more is TCP. And in TCP, there are two major functionalities, reliable transfer and congestion control. Okay. So we spend a lot of time talking about how we do reliable data transfer and congestion control generally, and how exactly they're done in TCP. Chapter 4 is the network layer, which is one layer lower. Okay, so what we're doing there is to try to make sure that messages coming from one host will reach another host. What TCP does is to ensure that messages from one process reach another process. All right, so in a way that what network layer is doing is a little bit more general. Okay. And so you can also see that getting messages through the network to another machine, what we will be doing there in the network layer is essentially passing data, and that is called forwarding. But how do you know which is the right way to pass the data? That is called routing. Okay, so forwarding, routing, these two are exactly the two major functions we are hoping to implement in the network layer. And if you recall the overview videos, routing, which requires implementing an algorithm, which could be a little bit extensive, that is done in the control plane, okay, the computation plane, okay, of the network layer. Forwarding is that for every packet we need to forward. Every packet coming, you need to forward. Guess how many packets will be forwarding every day through a router? Lots of them. So forwarding is something that should be really, really quick, okay? Taking hopefully no time to do, okay? So forwarding function is in the data plane. It's forwarding data, okay? So control plane doing routing, data plane doing forwarding. The operation scale is milliseconds in the control plane. The operation scale, the time scale I meant in the data plane, nanosecond, really, really fast. All right. But similar to transport layer, we have different types of services, right? TCP, more robust, UDP, best effort. In network layer, or sometimes it's called layer 3. So L3 service models here refer to network layer service models. So in the network layers, we also can provide different levels of services, different models of services. Okay. So the next two videos are to talk about the possibilities. Okay. So video number 1 is to still try to give you a little bit more background so you can imagine what service levels, what they are like in the network layer.
Before we talk about the service models implemented at the network layer, let me remind you this. If you recall, when we were talking about RDT, we say sending process, receiving process. If the underlying channel is reliable, all they need to do is just to pass data out and the data is just going to arrive. But unfortunately, the channel is not exactly reliable. Okay? And depending on how unreliable the channel is, the complexity of the reliable data transfer service is going to be different. More unreliable, more complex. Less unreliable, less complex. So the service model we'll be talking about next is to talk about how we implement. Okay, what kind of channel we're providing here? Are we going to provide a more reliable channel or less reliable channel? So more reliable channel is one service model. Less reliable channel is one service model as well. And we could actually have a spectrum of different service models here. There are two major camps of service models. First is the connectionless service. What it meant there is that the end hosts and the routers in the middle, they do not set up any connection-specific states before data being passed around. So there's no reservation of bandwidth, no reservation of memory space to buffer packets. So you see that there's not going to be any guarantee at all. Exactly. So this connectionless service is also called the best effort model. Okay. And this is exactly the model implemented in TCP/IP, the internet. The second camp, the connection-oriented service, which is the opposite. So the end systems, as well as the routers in the middle, they would actually exchange message and establish a connection before the data flows. So this is actually implemented in some of the old architectures, old systems. ATM, this is not the bank ATM machine, banking machine that you withdraw money. So this is actually a specific computer network that have been designed in the 20th century. At some point, ATM is actually competing with the internet. I think towards late 90s, still before the turn of 21st century, the ATM gets merged into the internet. So some of these routers in the internet, the lower architecture design is actually from ATM. Now, frame relay X25, these are just too old. But these are examples of connection-oriented network layer service. Now, to establish such a connection will involve routers, and the involvement is actually quite deep. It's complicated enough. It's the third important function, in these systems, on top of routing and forwarding. Now, one last bit I want to talk about is this. We've heard about connection-oriented service as well when we were talking about TCP, right? TCP, they're sending SYN ACK, and then ACK for the SYN ACK. That's the establishing connection, right? It sounded very much like these ATM frame relay X25 is doing. Yes. At the transport layer, TCP is actually establishing connection between two processes. At the network layer, in ATM frame relay X25, they are actually also establishing connections between two hosts. Right? But be careful. Internet at the network layer does not implement connection-oriented service. However, at the transport layer, implements connection-oriented service. So just be clear. Internet, the subject we're talking about and we'll continue to talk about, does implement connection-oriented service at the transport layer, but not at the network layer. Internet, in fact, when it is designed, it does have this complexity at the edge mindset so that we don't do complex things in the network layer involving the routers.
Now the second video, we'll be finally seeing different types of services at the network layer.
Yeah, those are the major camps. But within each camp, you can probably define finer service models so that you provide different levels of service. So, for example, we could actually come up with services for individual datagrams, such as guaranteeing the delivery of a particular packet, guaranteeing the delivery of a particular packet within 40 milliseconds. We could also try to provide services guaranteeing the flow of a number of packets. So we ensure that these packets will arrive in order, or we guarantee a certain bandwidth, or we restrict the time differences in between these packets when they arrive. So again, service models, they can be finer or coarser. It's more like a spectrum. Now what I'm listing here are the 5 services models that have been implemented and being used, at least for some time in ATM's case, and continue to be used today on the internet as well. So the internet service is, the best ever. So essentially it's not guaranteeing anything, no guarantee at all, and it's not giving condition feedback from the network layer. It's in fact being inferred from the transport layer between the TCP sender and receiver. Now ATM, quite sophisticated, provides actually a spectrum of service models. The CBR stands for constant bit rate service. So it actually guarantees a constant rate. So this is perfect for the constant data streams. It guarantees such that there's no loss, packet arriving in order, and the timing of the packets is also guaranteed. It's going to be constant. And there's not going to be congestion at all, so there's no need of congestion feedback. Variable bit rate service. So this is actually guaranteeing the maximum bandwidth required by a variable bit rate data stream. So there's no loss because we are guaranteeing to the maximum rate, right? So packet arriving in order, there's no delay as well, no congestion. So you see here, these two are highly guaranteeing everything, but one for the constant data stream, this one is for the variable rate data stream. Now these two, however, available bit rate service. So this is only guarantee a minimum rate. Therefore, there could be losses and the timing cannot be guaranteed because there's a lower rate. Packet could arrive faster than they can go out. So they could get buffer, they could get dropped at the buffer. But in ATM, even though there's no guarantee of the bandwidth delay, but there will be explicit congestion signal back to the data source. And UBR, on the other hand, in ATM, so this is the minimum level of service in ATM. It's called the unspecified bitrate service. So there's no guarantee of bandwidth, no loss. Packet will still be arriving in order. That's special about ATM because it's, after all, still a circuit switch network. And there's no timing guarantee, and in this case, no longer a congestion signal going back to the data source. So you see, again, network layer service model, it can be a full spectrum. Just that unfortunately in internet, or fortunately in internet, there's just one model we talk about, the best ever.
All right, so on the internet, it's very simple. We have just one model, no connection, best ever, which is what? Packet switching. So all these other models you hear about, these are from ATM, that is a circuit switched network. And next, let's talk about the router hardware, because the core of the internet, that's mainly where the network layer protocols are running. Well, on top of the host also run the network layer protocol, but most of the computation are really done on these routers. Okay, so these are forming the core of the internet. So let's check out the hardware components in a router.
Now let's take a look into the inside of a router. This is the general architecture. We do have a processor, which is doing the routing algorithm. So the complex route computation is being done here. The processor is quite high-end, very much comparable to the CPU, high-end CPUs we're using these days, except that the processor here might be a bit more optimized for route computation. Second most important entity, the switching fabric. Well, people will argue this is probably the most important entity because this is the part of the router that is doing the actual switching, the actual moving of the packets. And we know that the packet needs to be moved very, very fast. So these switching fabrics definitely needs to be high speed. Third, the input and output ports. Okay, by output ports, input ports, I actually meant that these network interface cards that we use to connect to the routers that are passing data in, passing packets in, as well as connecting to routers that we pass the packets out. You see then, the lower part is where the packets are flowing through. So this is the data plane, meaning this is the part of the router that we are flowing the data. So the functionality there, very important, just to move packets. In order to be very, very fast, the computation, the switching there, is pretty much hardware optimized. And so they can work in this time scale, the nano time scale. On the other hand, the upper plane, that is the control plane. Now we have the routing algorithm implemented as software running there. So in addition to routing, it does also a little bit of the management of the router. Okay? For example, tracking, monitoring, how many packets coming in, how many packets going out, things like that. Okay. Now, this part being implemented in software then operates in a slower time scale, the millisecond time scale. Now, one most important functionality for the router to do is forwarding. Now, it also does route computation here. Now, connection between the route computation and the forwarding here is this. After the route is computed, we install the forwarding table into the memory of the incoming network interface. Let's zooming a little bit more into the input network interface so that we see a little bit more the forwarding functionality. Where does it happen? And it's happening right here. Okay, the component that's connecting the input network interface to the switching fabric. Okay. So what's being done there is essentially switching, and it's done in a decentralized way, meaning for each of these input port, each of these input network interface, there's a lookup processor. Okay. So the forwarding of packets coming into each of these input ports is done parallel across all these input ports. So that's what they meant here, decentralized. So each lookup processor here is doing this. It looks into the header fields in the packet, and it's seeking the output port using a forwarding table that's installed from the route processor, and that is installed already into the input port memory here, okay, right here. The goal here for the incoming network interface is so that it can complete the input port processing, the lookup forwarding at the line speed, okay? Meaning, okay, if this is the speed of packets coming in, now this forwarding process needs to be fast enough so that we get the same output speed here. If this is slow and this is fast, so if this is R prime and R prime is smaller than R, then we'll end up having this. Okay, packet gets queued. Packets need to wait somewhere in a temporary buffer before they can go out. So that's queuing. Datagrams, if they arrive faster than going out into the switch fabric, then there's queue delay. Now, there are two different kinds of forwarding. In the traditional internet, we do the destination-based forwarding, which is to look at the packet header fields, particularly the destination IP address, and only the destination IP address. Now, in SDN, the modern routing, it's called the generalized forwarding because we can actually look at multiple header field values, not just one. And it can be arbitrary combination of these header fields. So it's a lot more general. But you can also see that provided the same lookup processor, okay, this is going to be a bit faster, and this is going to be a bit slower. So in order to keep up the speed, okay, if the incoming is R and output is R prime here, in order to make sure this R prime is as high as possible, usually in SDN, okay, these SDN routers will need a faster lookup processor here. So this one here, SDN routers, more expensive, while this one here, usually more affordable.
All right, so now let's look into further how forwarding is done.
So that was the router architecture. Now, there's one thing I want to talk about which is very, very relevant to the rest of the chapter. Okay. Destination-based forwarding. Okay. As you heard, forwarding is based on, for each packet coming in, look at the packet header field and try to match an entry in the forwarding table. Okay. So if the destination address says this, 11001000, matching this guy here, then we take this output port, okay, output link interface. If it matches, for example, this IP address, then we take output port 2. What happened inside this forwarding table is, if you think about it, right, there are so many possible destinations on the internet. And for each destination, there needs to be an entry, isn't it? So this is this particular destination's output interface being 0. So in fact, okay, in a forwarding table, you should be seeing for each possible IP address, what is the output link interface? For each of these IP addresses, what is the output link interface? But the thing is this, okay, how many possible destinations there can be? Well, the IP address is this big. Okay, the IP address, 8 bits, 8 bits, 8 bits, 8 bits together, 32 bits. So you could have actually 1 gig entries. And each entry might require, you see, 4 bits, 4 8 bits, that means at least 4 bytes, and maybe another byte here for the link interface. So each entry here at least needs to be 5 bytes. So 5 gig, 5 bytes, and that would be 5 gigabyte at least, just to keep the forwarding table. Okay, so the input port network card there, okay, it's gonna require not just a high-speed lookup processor, but also a lot of memory space. In addition to the buffer space might be required, right, in case queuing occur. So that particular interface there is already very costly. And if you need to have many input ports, many output ports, think about the cost of a very high-end router, very expensive. And that's not going to scale very well if we actually expand the IP address space. So this is a 32 bits IP address. This is IP version 4. Later on, you'll see. Okay, there's another version of the IP layer protocol. That's called the IP version 6. And the address space there is actually expanded to 28. So this approach, each IP, each entry, is not going to scale very well. So what's really being done on the internet is this. We do matching, all right, but not match the entire IP address. We only match the prefix, okay, of the IP address. So we're doing table lookup is to do matching, but we are only matching to the longest prefix. So this is what we do when we're looking up in the forwarding table entry. So given the destination address, okay, so we'll take this address and match the entries here. Okay. This time we don't have 1 entry per IP address. It's actually an aggregated or the prefix. So what you're seeing here is we only specify the first part of the IP address and leave the rest general. So that is also saying that as long as the destination address, the first few bytes match this pattern, okay, the rest of the IP address can be general, free. Okay. Now, as long as you have a destination IP address looking like this, then we take this packet to this output port. And the second entry is saying that okay, if the IP address matches this pattern, the rest can be flexible. No matter what, we go to output port 1. Now, there could be multiple entries. For example, this guy here and this guy here, you see here. Oh, up to this point, they are the same. So you could have an IP address matching both entries, isn't it? So in this case, we'll take the longest prefix. Okay, we'll take the entry that the destination IP address matches the longest. Now, in case the rest of the 3-bit of this IP address is 000, then we forward that packet to output 1. If it's something like 101, then it does not quite match this entry. However, matching this entry, then we send it to output 2. So let's exercise a little bit. Now, if we get a packet, the destination address is this. What should be the output interface? Let's see. The first 8 bits match. Great. In fact, all these 3 entries, the first 16 bits, actually 19, 20, the first 20 bits are all the same. So these 2 destination address, I think the first 20 bits are also the same. So what differs is beginning from the 21st bits. So which entry in the forwarding table does the first destination address match? Well, this is 0. So only this entry match, right? Because this is 1, this is 1. So these 2 not matching. Therefore, this packet goes to interface 0. Now, the second destination here. 21st bit is 1. So it should be either one of these. Now, 0, 0, 0. Well, it actually matches more the second entry. Therefore, the outgoing interface for the second destination address being 1. And that takes us to a double quiz time.
All right, so let's start with the quiz 30. Okay, first of the double quiz. So this is to try to test you whether you pick up longest prefix match. So what you are seeing here at the top of the slide is the routing table. We do have 3 entries. First entry takes the data to output port 0, second to output port 1, third to output port 2. All the rest that's not matching the first 3 entries will go to output port 3. So Q1 is to ask which output port this address, okay, 1100 all the way to the end. So I'm not gonna read the entire 01 string here. So find the output port for Q1 destination address, Q2 destination address, Q3 and Q4 destination address. All right. So please go now to the Slack space, channel W12, quiz 30. Oh, wow, okay. Yeah, so I see already Team 5 started working on it. And Team 5 says that IP address, that destination address in Q1 should go to interface 0. And Q2 should go to interface 3. Oh, all right. So actually, Polly has not yet worked on this problem yet, despite that she changed the destination addresses from previous semesters. So let's see. Let's see for Q1, right? So first, 8 bits matching all the entries. Second, 8 bits matching also all the entries. And then I think the first 4 entries in the third 8-bit, yeah, matches well to all the first 3 entries. So what differs starting from the 5th bit? So this is 0. Okay, so obviously Q1DA matches the first entry, therefore interface 0. So Team 5 there got it right. Okay. Let's see. Okay, yeah, more of you responded. Good. I see that some of you are taking your time too. Oh, okay, good. And you guys all came up with 0, 3, 1, 2. Okay, let's see Q2, whether it's going to port 3. Q2, first 12 bits matching. And then the first 3 bits in the third 8-bit match, but the fourth didn't match. So Q2 destination address did not match any of the 3 entries in the routing, first 3 entries in the routing table. Therefore, we take the otherwise interface, which is port 3. Very good. Okay, in Q3, I guess it's obvious by now. So for Q3, yeah, it matches all the way to the 20th bit. And then the 21st bit is 1. So the possibilities will be the second and the third entry, right? Does it match the third entry entirely? In fact, no, right? Because this is 0, 1. So 0, 0, 0, 1, 1, and then 0, 1. So it doesn't match the third entry. Therefore, we take interface 1. The fourth entry, 0, 0, 0, 1, 1, 0, 0, it matches perfectly the third entry. Therefore, we take interface 2. Okay. So for Q3 and 4 should be 1 and 2. Very good. All right. All right, so straightforward, longest prefix match. Now the second quiz. Okay, so given a bunch of destination addresses, right? If we write every destination address as one entry, we will have a lot of entries to match. Okay, so let's try to represent this table that has each IP address written now. Okay, even though many of the IP addresses share the same output port. And can we somehow simplify this and use the stars, okay, to represent the wildcard bits? Okay, so meaning we just need to match a certain pattern prefix, but the rest of the bits can be general. Okay, so let's work on this. And similarly, go to W12 quiz 31 channel on Slack. Given how fast you guys solve quiz 30, this should be relatively easy. So let's see. The fastest one gets bonus. Okay. but the first one who get everything right, of course. Well, you know what? I was right. It didn't take much time for you guys to come up with something. So let's see. Team 5, Jia Hong here had, okay, matching all the way to 2 more bits in the last octet, the last 8 bits. I think I had the same thing. And for the second entry, I do have it matching to the first 3 bits exactly of the third octet. Last entry, I match also the third octet and the first 7 bits match. Or is it the first 6 bits? I think it's 7 bits. Jia Hong, unfortunately, you did not get it perfectly right. But I think Team 2 got it. Yeah. 0001101 and then wild card. Very good. Yeah. So essentially you have the first entry having the last 6 bits being the wild card. The second entry, the last 8 plus 5, 13 bits. Okay, 13 bits. And the last entry you have the first you have the last 9 bits, okay, being the wild card. Great. All right. So trophy goes to the trophy. Where's my trophy? Okay, the medal. Medal goes to Team 2. Okay, but very well done. Okay, Jia Hong. Yeah, I think Team 6 got it as well. 00110 and 7. Very good. Team 1 gets it right as well. Okay. All right. I think you guys have already got it. Okay. It might take a little bit more time for some of the teams to type things out because some of you might be, a little bit of a clean freak, meaning you want to, align everything, okay, and so that it looks clean. Very good. Tai Tong, yes, very good. Okay. All right, so you've got it. Okay, let's move on with the lecture. Okay, so this is to summarize a little bit of longest prefix and to tell you how exactly fast matching, fast forwarding can be done on the routers. Okay, usually we use a very expensive kind of memory called TCAN.
Longest prefix matching is really nice because you see in the forwarding table there are so many less entries, right, as opposed to 2 to the power 32. So memory requirement at the input port less. Lookup process faster because again less entries to look for. So less memory, faster lookup, 2 methods. There's one more benefit that justifies why we use longest prefix matching. But we'll talk about that later in section 4.3, IP addressing. Now back to longest prefix matching. If you recall, we say In the lower part of the router, the data plane, what we do is to often use hardware to optimize all sorts of processing there. This prefix matching is performed this way, also using a specialized hardware called the TCAMs, ternary content addressable memories. Okay, the idea of this is this. It's not strictly a memory space. It's actually memory space with some computation circuitry. So the main circuitry there is a searching interconnected network. Provided the destination address, which is a prefix, this searching network allows it to go really fast and go to an exit point where the output port is stored. So the searching circuitry is fired really quick, okay, and taking the exit in one clock cycle. Now the part that is a bit slow is to insert the right port number at different exit points. And that is done when the routing processor finishes computing the route, when we're installing the forwarding table. So the installation of the forwarding table there using TCAN is to install is to assign the right port number at different exit point in this searching interconnected network. That is why when packet comes in, the searching part is really, really fast within one clock cycle. So the forwarding table installation is only one time, so it's not a big deal, okay, although longer. But for all the packets coming in, that's very, very frequent, very fast. Now, as you can imagine, TCAM is very expensive. Okay, Cisco Catalyst series there allow us to store 1 million of these prefix entries. So, very expensive router. And by the way, Cisco is one of the biggest router designers, router manufacturers. There are actually a number of these router manufacturers in Taiwan as well, like D-Link, like Asus. Yeah. But the routers manufactured in Taiwan are usually lower cost, okay? Good enough for maybe home use, maybe for access point use, maybe for enterprise use.
All right. And then that's check out the switching fabric, the component that's right in the middle of the router in the data plane.
Switching processing the data plane is also optimized by hardware. And that hardware is called the switching fabric. And the goal of the switching fabric is very simple, to move packets from the input port to the output port. And the key design metric is the switching rate. Now, one thing that one needs to be very careful designing a router is if we design such that there are n input ports possible, and the line speed of each input port is R, then you want to make sure that the switching fabric can switch at this rate, R multiplied n. Alright, so what we're seeing here are 3 different architectures of switching fabric. Memory is generation number 1, bus number 2, and the modern ones, generation 3, the crossbar architecture. Now let's go over them one by one. So first generation, switching via memory. The architecture of a router of the switching fabric is very much like a traditional computer, where we have a CPU, memory, and then hard disk. So we fetch data from the hard disk to the memory first before we fetch the data from the memory to the register, and therefore we fire the computation circuitry. So memory there is the middle point. Before data can go anywhere, you get it from the source, okay, before you push it out. So similarly here, we do have packet in the input port, and we want to push it to the output port. The packet is going to be copied to the system memory here in the middle, okay, like this, through the system bus. And then from the memory, copy them to the output port's memory. So the speed of moving the packets is limited pretty much by the memory here, okay? The speed to write and the speed to read. Now this is usually very slow, and the cost of the memory is also high. And not to mention this, we send packets into the memory like this, and we also fetch packets out from the memory like this. So you see each packet has 2 bus crossings. If the bus speed is R, the throughput can only be this much advanced. If this is not limiting memory's read-write access time. Therefore, in the second architecture, that's bypass the memory entirely, so let's remove the memory part, there's no middle point. Packet is copied straight from the input port memory to the output port memory like this. And as a result, we only have what? 1 bus crossing. That is saying the bus rate is exactly the throughput. And this is actually in the Cisco 5600 series. Having a 32 gigabits per second bus guarantees also 32 gigabits per second switching rate. Now the only limitation is just the bus. Okay, there could be bus contention depending on how many input ports you have and how busy they are. Last architecture is this interconnection network or the crossbar network. The architecture looks like this. So the input ports are connected to a network, and then output ports are exit points of the network. So you see potentially this. Yeah, these red lines are buses. Okay, bus speed can still be R. Right. But you know what? Data can potentially flow here, this pass. So you get 3 flows that can potentially go through the interconnected network in parallel. Although the bus speed is R, but you get triple amount of data through. Okay, so there's a certain degree of parallelism there we could exploit. So this design here, the crossbar design, or sometimes called the grid design. Okay, it could be 2-dimensional grid. Nowadays, 3-dimensional grids is also quite common. Okay, so we use an interconnected network there to try to speed up, add some degree of parallelism. Now, this design is actually not new. When people are designing computers where there are multiple processors, the multiprocessor computers, people have already thought about using this architecture to ensure the processors are well connected so that we could distribute computation tasks efficiently. We allow fast passing of the data from one processor to another so they can continue the computation from another computer, okay, another processor. Right? The last part of doing interconnected network architecture is this. We'll have to cut the bigger data gram into smaller cells, okay, and fixed size cell. It's very important it's fixed size. So yeah, the transmission of these cells is very fine-grained and easy to control because it's fixed. The time, duration, very stable, very fixed. So that avoids also contention on such a interconnection network. And therefore, Cisco 12000 is one such switching fabric-based router. It can switch about twice, okay, amount of data than the bus-based switch fabric.
Right. Now let's take a look at a few examples and see that there are actually options a switching fabric can implement as well. In some cases, the transmission of the packet, switching of the packets might be slower. In some other cases, faster.
There's one very important mechanism needs to be implemented in a router. That's called the buffer management. We'll need it in the input port as well as output port. Now, the reason that we need it in the input port is this. When the switching fabric is slower than the input port rates combined, the packets coming in really, really fast. And these packets might need to be queued temporarily in the buffer. That's why we see queuing delay. When the buffer is full, packet get dropped. So the queuing strategy and the dropping policy, as well as how much buffer we should allocate to this input port, those things are all part of the buffer management, which we'll talk more about in the next few slides. But before that, let's talk about this very special kind of queuing delay. It's called the HOL blocking. Now let's focus on the scenario. Okay? It's easier to understand that way. So this router here I'm illustrating has output port contention. So this is one special type of router. What it means there is each output port can only draw in one packet at a time. So this red port here is only taking in red packet, and it can only take in one red packet at a time. Similarly, for the blue port, taking in blue packets. Green port, taking in green packets. Now, the input ports, there are 3 of them. Input port number 1 here has a red packet at the front. Input port 3 here also has a red packet at the front. Now, this is what? An output port contention-based router. So we can only pick one of these to accept into the output port. Let's assume this one goes through and this one gets blocked. One packet time later, you see this red packet arriving at the output port. That's why we see the red packet here. This blue packet arrives at the blue port. That's why we see the blue packet here. But this one stays. Therefore, one packet time later, this red packet stays. But if you consider this case where the green packet's at the front and the red packet's in the back, then we could have what? One packet time later, the red packet, blue packet, as well as the green packets, all 3 of them move to the output port. So instead of receiving only 2, we could have 3 packets through. Isn't that better? Yes. So green packet in this scenario here, it gets blocked unnecessarily when they can really be moving forward. Okay, so that is called the head of line blocking. Green packet here experiencing a head of line blocking, head of line queuing. because other packets such as the green one is blocked by the red packet at the front. Okay? And somehow the output port is not accepting multiple packets coming in at a time. On the other hand, if you have a router that implements the non-output port contention mechanism, then we could have what? Input port 1, input port 3 both have red packets. They can now all go to the red output port. So one packet time later, you see 2 of them here. Okay? And the blue one will also go one packet time later. And the next cycle, then you see green, the next one in line in input port 1 goes to the green port. And the red packet here goes to the red port. Okay, so HOL blocking only occur in the output port contention type of router. So that was the divergence. Speaking of this very special type of queuing one might experience. Now let's come back to buffer management. We need also buffer management at the output port. And this is because the arrival rate through the fabric could exceed the output line speed. So switch here super fast, such as a non-output port contention router. Usually the packet can come in real quick. We could have red here, then all of a sudden we get 3 red packets coming in. And if the line speed here is slow, the buffer actually queued up real quick. It gets full real quick. So delay also gets long, and you might also have packet loss. And the buffer here also needs to be managed.
All right, so that was the video that transitioned us from the switching fabric to the buffer management that are necessary in the output port as well as the input port. Okay, tune in tomorrow morning. We'll talk more about buffer management. Okay, so there are issues you need to think about. If buffer is full, which packet do we drop? Okay, of course we could drop the packet that's incoming now, but one can actually select the existing packets in the queue and drop those as well. Okay. And forwarding the packets further from the output port to the next hop, one can actually pick some of the packets in the queue to forward first, as opposed to the first one in the queue. Okay. So those different policies one may consider implementing, managing the buffer. That's coming up tomorrow, and let's call it a day. Okay, you have actually 2 minutes left, in fact, to the end of the class. Feel free to type up in case you have any questions. Those who don't, just feel free to go. Okay, and I see you tomorrow. Bye. Okay, and Polly is gonna stay on for 2 more minutes at least, and see if we have questions. Yeah, bye. Yeah, and of course, if your team has not yet completed quiz 30 and 31, this is also the time best use to try to finish those. Then you don't have to worry about making the Saturday deadline. Oops. Okay, bye.